Welcome to the course. For centuries, we thought the stars, gas, and planets were the main event. We now know they are just the foam on top of a very deep, dark ocean. Today, we're going to look at the two phenomena that govern the structural integrity and expansion of our cosmos: dark matter and dark energy. By the end of this lecture, you'll understand why 95% of our universe is invisible to every telescope we've ever built. Look at this breakdown. This is our cosmic budget. Everything you have ever seen, every star in every galaxy, every biological life form, represents a mere fraction, about 5% of the universe. Dark matter provides the gravitational glue for structures, while dark energy acts as a repulsive pressure, pushing everything apart. We infer their existence not by seeing them, but by observing their influence on the geometry of space-time. Before we could find dark things, we had to map the light things. In 1912, Henrietta Swan Leavitt gave us a breakthrough: the standard candle. She found that for certain stars called Cepheid variables, the timing of their pulses is directly tied to how bright they actually are. If you know how bright a candle is, and you measure how dim it looks from Earth, you can calculate exactly how far away it is. This was the first step in understanding the true scale of the cosmos. While Leavitt was measuring distance, Vesto Slipher was measuring speed. He used a spectrograph to look at the light from distant galaxies. He noticed their spectral lines were red-shifted, meaning the light waves were stretched out. This meant these galaxies weren't just sitting there, they were moving away from us at high velocities. This laid the groundwork for the idea of an expanding universe. In 1929, Hubble and Milton Humason put it all together. They found that the further away a galaxy is, the faster it recedes from us. This is Hubble's law. Crucially, this doesn't mean the galaxies are flying through space. It means the fabric of space itself is stretching. This confirmed that we live in a dynamic, evolving universe, not a static one. Now we hit a problem. In 1933, Fritz Zwicky looked at the Coma cluster of galaxies. He calculated how much mass was needed to keep these galaxies from flying away from each other, their gravitational binding. He found a massive discrepancy. The visible stars and gas didn't have enough gravity to hold the cluster together. He proposed Dunkelmaterie, dark matter, as the invisible glue providing the extra gravity. Dark matter stayed a fringe idea until Vera Rubin and Kent Ford in the 1970s. Rubin looked at the rotation of individual spiral galaxies. According to Newton, stars at the outer edge should move slower than stars near the center, just like planets in our solar system. Instead, she found flat rotation curves. The outer stars were moving just as fast as the inner ones. This proved galaxies are embedded in massive halos of invisible matter that extend far beyond the stars we see. Einstein taught us that mass warps the fabric of space-time. If a massive object, like a cluster of dark matter, sits between us and a distant galaxy, it acts as a cosmic lens. It bends and magnifies the light, creating arcs or even Einstein rings. By measuring these distortions, we can weigh the dark matter, even though we can't see it directly. It's like seeing a glass lens on a white table. You see the distortion, not the glass itself. If you want the best proof that dark matter is a physical substance and not just a math error, look at the Bullet cluster. This is a high-speed collision of two galaxy clusters. The normal gas, in pink, collided and slowed down due to pressure, but the dark matter, in blue, sailed right through the collision without stopping. This shows dark matter doesn't interact with normal matter or itself via electromagnetic forces. It's truly ghostly. We can also see the fingerprint of dark matter in the early universe. The cosmic microwave background is the remnant of the Big Bang. It has tiny temperature fluctuations caused by sound waves in the early plasma. By analyzing the height of these acoustic peaks, we can determine exactly how much baryonic matter versus non-baryonic matter existed. The data from satellites like Planck confirms that normal atoms simply aren't enough to explain what we see. What is dark matter made of? Early on, we thought of machos, massive, compact halo objects. These are just normal baryonic things that are hard to see, like black holes or failed stars. We searched for them using microlensing, watching for them to pass in front of distant stars. However, sky surveys show there aren't nearly enough of them to account for all the missing mass. So we have to look for something more exotic. The leading candidate for decades has been the WIMP, the weakly interacting massive particle. These particles would only interact through gravity and the weak nuclear force. The WIMP miracle is a mathematical coincidence. If you calculate how many of these particles would be left over from the Big Bang, the density matches the dark matter density we observe today, almost perfectly. It's a very compelling theory, though we are still searching for them in underground labs. If WIMPs don't exist, axions are the next big contender. These are incredibly light particles proposed to solve a specific problem in quantum chromodynamics. Experiments like ADMX use massive magnets to try and catch an axion turning into a photon. We're also looking at sterile neutrinos and primordial black holes, but these remain more speculative for now. Now let's switch gears to the biggest mystery of all, dark energy. While dark matter is like glue pulling things together, dark energy is a repulsive force pushing the entire universe apart. Up until 1998, we thought gravity would eventually slow down the expansion of the universe. We were wrong. The expansion isn't slowing, it's speeding up. How do we know the universe is accelerating? We use Type 1a supernovae. These happen when a white dwarf hits a very specific mass limit and explodes. Because the mass limit is always the same, the explosion's brightness is always the same. In the late 90s, two teams found that distant supernovae were dimmer than they should be. This meant they were further away than expected, meaning the universe's expansion had picked up speed about 5 billion years ago. To explain this acceleration, we look back at Einstein's cosmological constant, lambda. He originally added it to force the universe to stay static, but today we use it to represent the constant energy density of empty space. In this model, as space expands, it creates more space, which contains more dark energy, leading to constant acceleration. In this scenario, the pressure-to-density ratio, W, is exactly -1. But what if dark energy isn't constant? Alternative theories, like quintessence, suggest that dark energy is a dynamic field that changes over time. Unlike the cosmological constant, quintessence can get stronger or weaker throughout cosmic history. This distinction is huge because it determines the ultimate fate of our universe. We are living in a revolutionary moment. Recent data from 2024 and 2025, specifically from the Dark Energy Survey, DES, and DESI, DESI, have shown inconsistencies. They found that the standard ruler of the universe, baryon acoustic oscillations, is 4% smaller than the standard model predicts.
This suggests that dark energy might be weakening over time. We are currently between 2.8 and 4.2 sigma. Not quite a discovery yet, but enough to make us wonder if Einstein was wrong. For the math inclined, this is the Friedmann equation. It relates the expansion rate of the universe to its contents. Notice the W term in the dark energy component. If W is exactly -1, we have a stable cosmological constant. If it's anything else, dark energy is dynamic, and we have to replace that constant with a complex time-dependent field. We measure the universe's density against the critical density, the exact amount needed to keep the universe flat. If omega is 1, space has no overall curvature. Current measurements confirm we are very close to 1. But remember our budget. Matter only provides 0.3 of that 1. Dark energy provides the other 0.7 to keep the universe balanced and flat.
Some scientists ask, do we really need dark matter, or do we just misunderstand gravity? Modified Newtonian dynamics, or MOND, suggests that at very low accelerations, like the edges of a galaxy, Newton's laws change. MOND is great at explaining individual galaxy rotation, but it fails when looking at larger structures like galaxy clusters or the CMB. And it definitely can't explain why the mass is separated from the gas in the bullet cluster. What is the end game? If dark energy is a constant, W equals -1, we face the big freeze. Expansion continues forever. Galaxies will move so far away they vanish from our view. Stars will run out of fuel, black holes will evaporate, and the universe will reach a state of maximum entropy, cold, dark, and empty. But if dark energy is phantom energy, W is less than -1. It gets stronger as the universe expands. This leads to the Big Rip. Eventually, the repulsive force becomes so strong it tears apart galaxy clusters, then solar systems, and finally it shreds atoms and subatomic particles themselves. It is the ultimate cosmic shredder. If dark energy weakens or reverses, gravity could win the tug-of-war. The expansion would stop, and the universe would contract in a big crunch. Some theories even suggest a big bounce, where this collapse leads to a new Big Bang, and the cycle starts all over again. We are moving from the discovery phase to the precision phase. 3 major telescopes are coming online. Euclid is already scanning the sky. The Vera Rubin Observatory will image the entire sky every few nights. And the Nancy Grace Roman telescope will give us the highest resolution view yet of the early universe. These tools will likely give us the final answer on whether dark energy is a constant or something much more complex. To wrap up, dark matter builds the structure of the universe, and dark energy determines its fate. We stand on the edge of a paradigm shift. The next few years of data might rewrite the textbooks you are holding today. Any questions? And thanks for watching this course.